Okay, it looks like we're ready to start. Good morning, everyone. My name is Jason Gregory. I'm one of the lead programmers over at Dialog. And today, I'm going to talk to you guys about the character dialogue systems that we developed for The Last of Us. Now, The Last of Us, the AI in The Last of Us was really entirely revamped over the AI that we had for Uncharted. I mean, we brought over some of the technology, but a lot of it was reworked. And one of the big reasons for that was that we really wanted to emphasize stealth gameplay in this game. We needed a slower pace. We needed something that fit more into the world of The Last of Us. And as a result of that, the AI characters are on screen for a lot longer. They're doing a lot more interesting behaviors than you might see in a game that's at fast-paced like Uncharted. There's been a number of good, really great talks on all of this. I hope you guys checked out Travis McIntosh's talk yesterday on the enemy AI for The Last of Us. And this afternoon, Max Dieckhoff is going to talk about the buddy AI, which is an equally fascinating talk. My talk's going to focus in on how that sort of intersects with Dialog and how Dialog supports both of those AI systems. There's also a great talk by Jonathan Lanier on audio technology. Unfortunately, if you're here, that means you're missing it. I'm sorry. It's right across the hall. If I get really boring or if you're falling asleep, I guess you could just go over there. I don't know. But anyway, so I definitely recommend checking it out on Vault. All right, so let's take a look at some of the requirements of the dialogue system for The Last of Us and how they differed from the requirements on Uncharted. So first, let's take a look at where we came from. In the Uncharted series, the AI, while it was a lot of fun and very addictive to play, it was really relatively simple in terms of its overall state machine. There were really only two states. The AI were either unaware of the player, doing some ambient behaviors, or they noticed the player and combat broke out and all hell broke loose. Now, because of this, the dialogue system in Uncharted, it was a reasonably complex system, but it sort of limited in scope because we only had to play individual lines on individual characters. So during, for example, an in-game cinematic, we might ask a character to say a line, or there might be a back-and-forth conversation, but it would be very scripted out, and it would always play out the exact same way every time. And in battle, we would have battle chatter, but again, it would just be individual AI characters calling out lines like, I'm out of ammo, or I'm flanking him, or there you are, airplane man, or whatever line that we chose. So because of this, we set up an API that was basically a fire and forget system, where you could play single lines on single guys. And we had a number of systems that allowed us to provide a wide variety of different character voices for those characters, and things to prevent them from saying inappropriate lines at inopportune times. For example, playing a hit reaction, you don't want the guy to say, I'm out of ammo, while he's reacting to getting hit by a bullet. So how does this differ in The Last of Us? Well, the AI state machine is about 2 times as complex in that we have now 4 states instead of 2. But more importantly, it's possible to transition back and forth between these states. So for example, when they're unaware of the player, they're doing their ambient behavior, the player can, for example, throw a brick or a bottle and distract them, right? And when that happens, they notice it and they'll go and check it out. They'll say, what was that? And if they don't find the player over there, they'll just return back to their ambient behavior. So this means that the characters are on screen, obviously, for longer, and we need them to do something interesting during that time. So we have to have them be capable of having a dynamic conversation that's interruptible. Now, once combat breaks out, we have a similar kind of 2-state system where there's full-on combat, where they're aware of where the player is, and they're actively trying to kill him, trying to shoot him, trying to close in, flank, melee, and so on. But the player can lose the AI. They can break line of sight, skirt around to another side, and the enemies will close in on the position that they believe the player to be, and they don't actually cheat when they do this. They think that he is wherever they last saw him. And if they get there and find that he's not there, what do? Well, they then go into a search behavior where they start trying to ferret out the player. And again, search and combat can go back and forth. Also, the buddy AI in The Last of Us was even more important than it was in the Uncharted series. And as a result of that, the buddy AI required a lot more rich dialogue, and we really needed to cement that relationship between Ellie and Joel. So the dialogue system was pushed to its limits in that way as well. So here's sort of a list of the requirements of our new dialogue system as we started to approach it for The Last of Us. Things like being able to telegraph the state changes of the AI, being able to provide conversations between enemies that can be interrupted and that can be dynamic based on what the player has actually done. They can actually react to the player's actions. We also wanted to provide location cues. Now, so this is very interesting. In The Last of Us, as you know, because you can skirt around and positions of the enemies is a very important thing. We needed to, A, telegraph where the enemies are to the player, and B, we wanted to sort of telegraph their perception of the player. So when they notice him, when they've lost him, and so on. And the positioning of audio became very important. Now, Jonathan's going to be speaking about a portal-based system that we did with our audio, which allows us to model the fact that, for example, if a sound is emitted in a hallway and there's a door down the hall, you actually hear the sound from the door, not from the direct line path. I won't talk about that in this talk, but it's a really neat technology. You should check it out on the Vault when you get a chance. What I will talk about is a location-aware dialogue system that we implemented where characters could actually call out Joel's location in a very specific way, and it's pretty interesting. So let's take a look at just some examples in-game of the various roles that dialogue plays, and just watch for the text that's overlaid on the video so you can know what to listen for.
Yeah, so I should have known better. If you're going to steal, then you better make sure you get away with it. Right? I would have done.
They're all dead! They're all fucking dead!
What the hell's he yapping about? Take a breath. Who's dead?
South clear!
North clear. Hold your position.
All right, listen! You don't need to do this! What was that?
I'll check out this area.
He's in here!
Really killing her? David said he wants her alive.
He doesn't get to make that call. James told me it's the girl from the university. How many of our guys were killed there?
Oh, shit. I didn't know that was her. Screw David, then. I ain't taking a chance with this.
I hear hunters.
Yeah, me too. Just keep it down while we're going through this area, okay?
We're up all night.
Turn around! Let's go! Look out! I got him!
Are you all right?
I'm trying to learn how to whistle.
You don't know how to whistle.
Well, does it sound like I know how to whistle?
All right, so that hopefully gives you a little flavor. By the way, that bit with whistling was actually invented by Ashley Johnson, the actress who plays Ellie. It was a great sort of ad-lib thing that she did, and she developed that whole thing about learning to whistle and added it to the story. It was really, really a great addition. All right, so let's take a look at how we can play and define and play lines of dialogue. And the first bit of what I'm going to talk about is very similar to what we did in the Uncharted system, and then we'll look at how we kind of extended the system for The Last of Us. So the core of any dialogue system, if you think about it, is it's translating logical events in the game that require dialogue to be played and translating those into physical lines of dialogue that are actually played, so the actual WAV files or VAG files or whatever that are played. And in doing that translation between a logical line and a physical line, a number of things happen. So first of all, there are usually multiple physical lines for any given logical line. So if the logical event is I'm out of ammo, the character might say, I'm out, or I need more bullets, or something like that, right? There's a bunch of variety involved in what they're going to say. Secondly, we need to shunt it to the right character voice, and I'll talk about that in a moment. We also need to avoid repetition when we're randomizing the lines of dialogue. And we need to prevent inappropriate lines from playing, such as I said, saying something nonchalant while you're in the middle of dying. Now, in any game that has enemy AIs that are coming in waves and so on, you need to have different kinds of characters that look different. And the way we did that in The Last of Us is by piecing together our characters using multiple meshes. So we had multiple head meshes, multiple shirts and pants and hats and all sorts of things. And they could be sort of randomized together to produce a wide range of characters. Now, the trick, though, is you want to see that same character. If you see that dude with the hoodie, you want him to sound the same every time you see him. And so what we do is we use the head mesh that was selected as part of this random selection to pin down a particular voice actor that is going to speak for that character. In Hunter City, or Pittsburgh, we had only 8 voice actors that were sort of recycled. And that makes sense. Every game has to do this because there's no way you're going to hire hundreds of voice actors to mimic every single character. But if you recycle a relatively large number like 8, it works out pretty well. So here's how we actually define things. I'll show a little bit of syntax. Obviously, our specific syntax doesn't matter, but it should give you an idea of the flavor of how we define things. This is just a simple text file that gets read by the engine. It can be loaded, reloaded at runtime, so rapid iteration is possible, and so on. So here we're defining a line of dialogue, line out of ammo. And we can specify different sets of lines for different characters. And then here are the physical lines, and these would be the names of the actual audio files that are getting played, the audio streams. And here's Ellie and her lines. And of course, we might do the same thing for hunters. In this case, this logical line applies to both the buddies and the NPCs, so maybe we'll provide lines for hunters A through H as well. Notice here, though, that the same physical lines are getting played. It's just that it's Hun A, Hun B, Hun C, down to Hun H. And that's because the 8 voice actors would record the exact same wording of each line, and that way any character could say any specific physical line. Pretty simple. One point of practicality, we like to break these data files up by character, by level, and this allows us to have different audio designers working on different aspects of the dialogue without stomping on each other. So breaking things down like this is very useful. All right, so one might ask, well, how do you play a line of dialogue? Oh, let me show you. I wanted Troy to record that for me, but oh well. OK, so basically, if your API for playing dialogue in your engine is really, really simple to use, it'll get used a lot. If it's complicated, the AI programmers will shy away from it. The designers won't use it. So you really want something that's simple. And we chose to do something that's just a fire and forget kind of API. Excuse me. So here's an example. In one of our so-called state scripts, this is our scripting language. The syntax doesn't really matter, but notice that it's an event-driven scripting system. So let's say in this case that the player sees a ladder. And so we have ladder seen because he walked into a region where he's noticed this ladder. We have Ellie maybe move to a particular location and wait for a few moments. And then we want Joel to say a line of dialogue like, hey, we could use that ladder. Now here, we're calling a function called waitSay. And the idea here is that the script actually goes to sleep as soon as that line of dialogue is triggered, and it only wakes up again when the line is done. This allows us to not have to hard code durations into our script. It's just naturally going to wait for however long that particular audio line is. And that also works for internationalization, right? Localization, where the line might be very different in length for the different languages. Here, however, we don't want to wait. We want to just say the line and then go on with the script. Maybe we want Ellie to speak while she's doing her move to command here. So we have both choices in script. In C++, we only provide one of these 2 variants. That's the one that doesn't wait, because there's not an easy way to put our C++ code to sleep, and it fits more naturally into the AI code to be able to just do these fire and forget calls. If you do want to wait for a line of dialogue to be done in C++, there's an event that's called when the line is done, or you can simply sit there and poll and ask the character, hey, are you done yet? So it's pretty straightforward. Obviously, just a few implementation details. When a character has multiple physical lines that they can say for any given logical line, we need to prevent repetition. And we might also want to control probabilities of these lines. So let's just look briefly at how we do that. Again, it's very straightforward. What we do, now what you could do, right, is you could just call rand, right, or whatever your randomization function is in your engine. The problem with that is it'll give you a random selection of lines, but it very easily could provide or produce repetition in those lines. So what we did is we just pre-shuffle the lines and then play them in order, just play them sequentially. And the only thing you need to do is anytime you make a new shuffle, you just have to make sure that the last line that was played of the shuffle order doesn't match the first line of the new shuffle, and then you never have a problem with repetition. Now, you might want to provide some probabilities. In this case, we need a different mechanism for randomization, and we do have to check explicitly for repetition. But so basically what we do, and most programmers do this naturally, what they might not realize is that they're actually calculating something called a cumulative distribution function, or CDF. That'll make your math teachers happy, but you don't have to worry about it. Basically, all we're doing is we're taking the probabilities of the lines in some predefined order and adding them up and creating a stair-step function like this. Right? So if the probabilities are 0.2, 0.2, 0.35, and 0.25, that's our stair step. Then we calculate a random number from 0 to 1, and if we just search down until we find one whose cumulative probability is less than that value. So in this case, we choose A, but in this case, we walk along and we eventually choose C. Pretty straightforward. Okay, so I mentioned that we have to provide a way to prevent inappropriate lines from playing. And the reason for this is that we're going to be retrofitting these dialog requests into our existing AI code. Usually, you don't know what kinds of dialogue you want until the AI is solidified. And the AI, I mean, anybody who works on games knows that your AI is going to change over and over. You're going to be iterating right up until the last few months of development a lot of times. And so you need to be able to just pop these things into your AI code at appropriate locations. That means that there might be lots of conflicting requests coming in at the same time. You might have one bit of AI code that's saying, hey, I want to say my normal ambient line of dialogue, and meanwhile another one is saying, no, I just got hit by a bullet, so play the hit reaction. So the way we resolve this is by simply giving lines priorities. This is a simple example. We actually have a slightly more complex priority system than this just to deal with certain special cases. But basically, you have efforts at the very lowest priority, things like grunting when you're vaulting over something or jumping. You have AI battle chatter. You have in-game cinematic things that actually trump the battle chatter if it comes up. Hit reactions trump that. And then, of course, if you're dying, there's not much you can do except grunt and say your last words. All right, and so the priority system just works like this. Very simple. Line 1 is playing on a character, and if a lower priority line comes in, it's rejected, and if a higher line comes in, it'll interrupt. Straightforward. You might be wondering, well, wait, how do you make an interruption sound natural? And we actually, in a way, kind of overthought this a little bit at first. We talked about a bunch of different ideas, like trying to do a glottal stop, right, which is where you sort of suddenly stop speaking, or perhaps having lines overlap and having one character show some indignation at being interrupted and so on. But at the end of the day, keep it simple. It turned out that by just cutting off the line of dialogue abruptly, it worked great for most of our situations. Now, your mileage might vary. It depends on the type of game. But usually you're in a heated battle, and just cutting it off is all you need to do. All right, so let's look at how we evolved this for The Last of Us. We needed, as I mentioned, to provide conversations, and we wanted them to be interruptible and so on. So let's look at a few examples in the game of this, and then we'll see how we did it. Oh, I'm sorry.
What was that?
Oh, no. Ellie, get down.
Where did you learn to shoot?
Man,
You had an entire flock and you hit nothing.
I'm about to hit you.
Wow. Yeah, you're really upset. Well, if you want some lessons, I'm more than willing to help you out.
Yeah, whatever. It's down! Finish it!
I got it!
Nicely done. You bit?
Not today. You?
Not today.
The fuck? I heard something!
Hey, careful, all right?
All right. So a conversation is actually relatively easy to do, you would think, and it is, but there are a number of things you have to take account of when you want to support interruptions in conversations. And so we chose to do it a way that allows us to do some of the more complicated things we wanted to do. So here's a really simple conversation. We've got two different characters back and forth just speaking some lines. And the way we would define that is by using another data file that actually splits the conversation out into segments or individual sort of lines in the back and forth, and links them together. So here's a conversation with 2 segments. And here's the line that we would play, and that maps to the other data structure that I was talking about before. So it's a logical line that can branch out into different characters and so on. And then a next segment that links things together. And just using a very simple system like this, you can do really straightforward conversations. You might say, well, that doesn't really add much, right? It doesn't give us much. However, there's this little thing right here, rule. Now, so here's the thing. When you're doing a conversation where it can't be interrupted and it's always going to play out the same way, you can just have your game designers script it out. Or you can even have an AI programmer script it out if you want to. But when your AI logic gets more complicated, you don't want your AI programmers embedding all sorts of lines of dialogue in there and dealing with the timing of, OK, line 1 has to be said, and then line 2, and then line 3. And also, when things are interruptible, your conversation might branch out in interesting ways. So you can't really do that in a game like The Last of Us. So what we did is we actually got some inspiration from a great GDC talk, GDC 2012, by Elon Ruskin of Valve. They had implemented a really neat-looking rule-based system, and we decided we would take some of those ideas and integrate them into our system. So I highly recommend you check out this talk on the Vault if you can. Or actually, no, it's on Valve's website, so you should be able to get access to it. All right, the basic idea of their system, and the one that we've used in The Last of Us, is to allow audio designers to write rules. And these rules are just simple expressions, the Boolean expressions that evaluate to true or false. And they're written in terms of something that we call facts in a fact dictionary. Now, we could have just said, you know what, we're going to provide a scripted interface for this, and we'll let the sound designers call any function in the engine that they want in order to get data from the AI. But that leads to a number of issues. First of all, it's sort of a daunting task for the sound designers who really didn't have a lot of scripting experience to have to learn the entire scripting language and figure all that out. Number 2, it gives them not an easy way to sort of see what's available to them. And it's also got some performance implications if you're allowing them to call things that might be, might have a big impact on performance. So by taking the information that's relevant to dialogues and put it into a fact dictionary, it allows the engine to control the cost of updating those bits of data. And it also provides a nice sort of palette of information that the audio designer can choose from when they're writing rules. So here's an example of a fact dictionary. It's just a simple key-value store. So here's the keys. Here's the values. Each value carries with it a data type. We actually store them as something we call a boxed value. Basically, we just support only 3 very, very simple data types: integers, floating point values, and string IDs. And a string ID is really just a hashed string that's been turned into an integer, right? So, for example, this tick hunter here is really just some hex number, internally. We use a single tick in our scripting language to represent these string IDs, so that's why you get these little ticks in front of everything. And of course, the keys in the dictionary are all string IDs. All right, so a rule then is really just a collection of criteria, and each criterion is really just a fact ID that tells you which fact you're checking, and some operator, comparison operator, and some hard-coded value that you're checking against. So here's a really simple example. Health. Maybe my health has to be more than 50%. Maybe this only works in Hunter City for some reason. And it only works once the enemy count has been reduced to less than 3. Now, these individual criteria are combined using a Boolean AND. And if you want to do an OR, as I'll show you, you can just branch out into other conversation segments or have multiple rules inside a single conversation segment. Now, we actually support a couple of different kinds of checks. We can do an existence check, just is this key in the dictionary or not? I don't care the value at all. I just want to know if it's there. We can also do integer equality checks. But you can't apply these to floating point values. We did this on purpose because, as most of you probably know, right, if you try to do an equality check on a floating point value, they might be almost equal but not quite, down to that one last bit in the mantissa, and then the sound designer doesn't know why it's not working all the time. So we restrict this to integers. And for integers and floats, of course, you can do range checks. And we support simple less than, greater than, and min-max kind of range checks. All right, so here is a little example with a rule. And we just select different lines based on whether the speaker is Joel or Ellie. And here's that in the game.
Get him! Here she is!
All right, so that's really super simple. But when you combine this with the ability to chain segments of conversations together, as you can well imagine, you can do almost anything that you can imagine. You can set up branching conversations with almost any kind of graph that you can think of. And so here's another example of that where we're just based on the number of enemies that are currently alive. If there's only one guy left, he's going to say something different. But if there's multiple guys, it actually branches out into a small conversation.
Damn it. He's got to be around here somewhere. Fuck. I'm going to check out this area.
Hey, you guys, search around in here.
Where you at, motherfucker?
I'm going to find this asshole. Come out, you coward.
And I should mention, too, that you can have rules inside your conversation segments that don't actually play any lines of dialogue at all. So this is a way to just create more complex logic where you can branch here and here and here before you even get into actually playing lines of dialogue. So this was a super useful feature that we added a little bit later into the development, but it gave the auto designers a lot of flexibility. Okay. So I mentioned fact dictionaries. We actually don't just have one. There's actually a number of them. There's a global fact dictionary that just contains information that's relevant to any character in the game, like what's the current level that we're in, or how much time has elapsed since the last time the player died, these kinds of things. And then we have one dictionary per faction. We group our AIs up into factions, as most games do. So we have Joel and the buddies sharing one dictionary. We have one maybe for the hunters, one for the infected, and so on. And then, of course, each character can have their own fact dictionary. Then this stores information specific to that character, like his current health or what weapon they currently have in their hand, that kind of thing. And at runtime, we can display which facts they have. You can see that Ellie actually has a lot more facts than Joel. The reason for this is that Joel, being the player character, actually has less complex dialogue and conversation than his buddy counterpart, Ellie. Ellie's conversations can be quite involved. So you need more facts to be able to do that. Now also, when we're requesting a line, a logical line like spotting enemies, for example, let's say Ellie has spotted some enemies, we want to provide context information about that event. So we might want to know how many enemies we're seeing. And in addition, we want to know who's speaking and who else is involved in that conversation. So in this case, the speaker is Ellie and the listener is Joel. And we call this the context dictionary, and it just fits in the same way that any other fact dictionary does into the system. I should mention one other thing, just a minor point about syntax, that just to make these examples make a bit more sense. Here you can see that we're actually specifying the fact ID not as a single string ID, but actually as a pair. And this is the dictionary ID and the key. That's necessary, right, so we know which dictionary we're looking in when we're picking out a fact. And there's our operator and the value we're comparing against. So these are some of the valid dictionary IDs, global, the faction name or the name of the character in particular, or tick context. And as I'll mention in a moment, tick context, the character name can actually be speaker or listener. There's a couple of magic keys that we have, and I'll show you how that works in a second here. One other thing is you can actually omit the dictionary ID in certain cases. So global facts, these two are equivalent. So global level and tick level are the same. And the reason for this is that we actually just do a simple search in both the context dictionary and the global dictionary for a fact if you don't specify a dictionary ID. And this is just a shorthand, but it makes the life of the designers a lot easier for very commonly used facts. So here's another example, context speaker. We almost never write it that way. We always just write it as tick speaker because it's sort of implied that it's going to come from the context dictionary. Okay, so speakers and listeners. The trick is when you're writing these rules of dialogue, you're inclined to just type in the name of Joel or Ellie. And when you're doing a buddy conversation, that makes sense. And maybe it will always be Joel that speaks and always Ellie. But how do you do a conversation with enemies where the names of the enemies might be something like NPC HC for Hunter City -07 or something? You don't want to hard code those numbers directly into your rules because then that rule only works for that particular character in Hunter City. You want something more generic. And so what we did is we introduced these magic keys called tick speaker and tick listener, and they are simply looked up in the context dictionary like this. And then we sort of at runtime just replace it with the name that we find there. So this allows us a little one level of indirection that allows us to write generic rules in terms of speakers and listeners. Now also, the conversation will ping-pong back and forth like this.
Oh, I'll be checking in for one night, and I would like your finest suite, please.
The hell are you doing?
Why, yes, you can take my luggage upstairs.
You are a weird kid.
And so the nice thing about using a fact dictionary for this is that we can just ping-pong back and forth the values in the context dictionary as the conversation progresses. And the other thing about this is that the designers, the sound designers, actually have control in their rules of which character is going to become the speaker or the listener for the next line of dialogue. So it allows them to completely craft the conversation without involving an AI programmer, all just using the data in the context dictionary. And actually, a little note here, we actually support listener B and listener C. Tick listener is really just listener A, but to keep it short. And this allows us to do up to 4-person conversations. I should point out one key difference here between our system and the system that was outlined by Valve in 2012. So Valve's system, in a way, is a bit more ambitious than what we're trying to do in that they evaluate every single rule in the entire engine, every rule that you've defined, pretty much every frame, or they'll load balance it over many frames, but they're sort of constantly evaluating the rules. The idea being that anytime any rule becomes true, boop, it'll trigger some action, right, like saying a line of dialogue or maybe some action inside the AI. And that's really cool, but it's also, as Elon mentioned in his talk, it's sort of a daunting task to make sure that the rule evaluation is super, super efficient because you're evaluating thousands of rules, very often during your game. What we decided to do is something simpler and just make it an event-driven system. So what we do is anytime a line of dialogue is requested by the AI code, then and only then do we evaluate the rules for only that conversation segment and the subsequent segments as they play out. So this just really shrinks the amount of time we need to evaluate rules and allows us to do maybe even a little bit more complex things without having to worry about performance. So for example, right here, wait say, that's when we're evaluating the rule for that particular conversation, and same here. Now in C++, we have one other thing that we can do, and actually this is exposed in script too, but it wasn't used very often, and that is to define a context dictionary. And to fill in whatever information you need. So as the AI code is firing off events, it can just embed a little chunk of code that says, oh, and by the way, the number of enemies in this case was whatever. So that's how we pass information down. And once that context dictionary has been created, it persists and it gets passed down to every element of the conversation as it goes. All right, so if you've got a bunch of rules inside one conversation segment, you need to figure out or you need to figure out a way to resolve ambiguity. So let's say that you have 2 rules that are both evaluating to true, or 7 rules that are all evaluating to true. How do you deal with that? Well, we do just what Valve did, which is we choose the most specific line of dialogue. And the way you measure that is just by counting the number of criteria. It's a really simple measurement, but it works really well. So here we have 3 criteria and only 1. Both of these rules would be true, because let's say that it turns out both of these rules are true. Then we would obviously choose the one above with more criteria. Now, if there's the same number of criteria, we simply treat that as a random choice, right? So in that case, these 2 rules are both true, and we will choose either line random 1 or line random 2 using a shuffling technique or whatever randomization you choose. Now, there are some cases that arose where we wanted random choice between 2 lines, but the number of criteria weren't equal. And so all we did is implemented a little dummy mechanism that allows us to cheat the number of criteria up so that it'll win, right? And then you can get a random choice out of something that otherwise would have not been. So that's just a little cheat we do there. One other thing I should mention is there are certain kinds of information in a fact dictionary. I mean, the problem with fact dictionaries, right, is that the data in there is sort of static, yeah? You store the data in there, and that's it. But in the case of, let's say, timing data, as an example, we can store the last seen time as an absolute clock value. Let's say that we're counting the number of ticks, where a tick maybe is 1/300th of a second or something, since that encounter has played. Well, you aren't going to write a rule that's based on an absolute time value. What you really want is how many seconds have elapsed since between now and that time. And so you need to do a subtraction, which you can't really do in the rule system. So all we did is we implemented various little operators that you could wrap around your fact values, like seconds since, that does the calculation for you. And it turned out that was all we really needed. One last thing to mention about this system is that we have what we call rule side effects. So anytime a rule evaluates to true within a conversation segment, whether it plays a line of dialogue or just branches off to another segment, we have this on play, which is an arbitrary chunk of script code that can do whatever it wants. And one of the things it can do is it can store information into fact dictionaries. So this allows rules to be self-modifying or to sort of update as things go along. And so this allows us to, for example, say the first time a line plays, do one thing, and then store that value in the dictionary saying, yep, we played that line, and now the next time around it'll be different. Or we might increment the number of times that it's been done, or these kinds of things. But it's an arbitrary piece of script code, so you can do anything you want here, including sending messages to the AI or triggering an in-game cinematic or whatever you want to do. And by the way, all it's doing is just looking up in the context dictionary, and then that value is getting read back. So here's another example of just what this rule system allowed us to do. In this case, depending on the player's actions, the conversation here is going to play out quite differently.
Hey, you got a second?
Yeah.
I just want to say I'm sorry about Tess. That's it. I won't bring it up again.
Ellie, you don't need to worry about me.
Hey, you got a second?
Not right now, Ellie.
Okay.
So it's a simple example, but it gives you a flavor of the kinds of things you can do. Now, when you have a system like this, very quickly you put this in the hands of the audio designers, and it gets crazy because they love it. They start filling it up with huge amounts of data. And pretty soon you've got tens of thousands, hundreds of thousands of lines and thousands upon thousands of rules. So how do you manage all that, and how do you debug what's going on? Well, we just implemented some very simple tools at runtime. And this is just something we always do. I guess every developer does it, just to allow us to see what's going on. And one of the simple things we did is we just log a bunch of details about each request that's coming in and whether rules are passing, or if they're failing, we actually print out why, like which fact was responsible for that line failing. And there's also the context facts are printed here, and you can see the other facts at runtime like this. So using just these simple tools, you can pretty quickly figure out what's going on. One other thing we did is in our in-game menus, we set up a system where every conversation, literally that's defined in the entire game, was available in the menus to play. So you could go and select a character and just tell that guy to say a certain line of dialogue. So this is really useful because sitting around waiting for the AI to do what you want it to do can sometimes be frustrating and tricky. And so just play it and see if it works properly. That usually works, although there are some issues with, if the facts aren't correct in the dictionary. So we had a few systems for allowing them to play like a script that would set up a certain set of facts, and then you could test that scenario. I did mention interruptions in our conversations, and I wanted to show you a little example of that and talk a little bit about some of the idiosyncrasies of getting interruptions to work properly when you've got multiple people involved in a conversation.
Oh, shit. Get down, get down.
How many is that now?
5 just this week. Hey, I'm not complaining.
I bet you.
Hey, what was that? Yeah, what the hell was that?
All right, so using the system that we did for Uncharted with the priorities still works, but there's a few things you need to take into account. So let's imagine first that we have a two-person conversation, and a line comes in. This is just like the Uncharted system. It's at a lower priority. It's overlapping the person who's talking, and so we say, no, sorry. And likewise, down here, lower priority, bye-bye. If a line comes in that's higher priority, we interrupt. But we have to interrupt the entire conversation, or, well, not always. So this is an interesting point, too. Sometimes you want to just cut off the whole conversation. Let's say it's that we noticed the player. We were having an ambient conversation like you just saw. And if you notice the player, then everything, you just want to cut it off, and boom, you're right into the combat. But in other situations, you might want the other character to continue. For example, let's say the player does a stealth kill on one of the guys. And so we actually have situations where there'll be a back and forth conversation going on. You stealth kill one dude, maybe while the other one is talking. And then when he's done, he sort of waits for a while for the other guy to speak. And if he doesn't hear the other guy speaking, we actually send events back and forth to say, yeah, okay, the other part of the conversation was played. If he doesn't receive that event, then he actually branches off in another part of the conversation where he goes, dude, you okay? What's going on over there? And then he'll go and investigate. So sometimes you want to interrupt, sometimes you don't. But the key here is that you need to track at runtime all the people that are involved in the conversation. That's why we have speaker and listener in the context dictionary. So the system actually has a concept of the conversation as a whole, not just the individual lines. Likewise, if lines come in while one of the characters is waiting for the other character to say his line or her line, we want to apply the same kinds of rules. So here, this is rejected because the other character is speaking. And likewise, here, it's a higher priority line, but because it's coming on top of the conversation as a whole, it still interrupts things. OK, so in a nutshell, that's what we used. That's the technology. It's not super complicated. It's not rocket science. But giving our audio designers the tools they needed allowed them to just go crazy and really flesh things out in a realistic and awesome way. But if you've got really great conversations and they don't sound good in the game, they don't sound grounded in the environments, then it's not going to work. It's not going to sell. So I want to talk a little bit about some of the things that we did. And as I mentioned, Jonathan Lanier's talk will talk in a lot more detail about some of these things. But I wanted to give you a feel for it. One of the first things you're always going to do when you're doing a 3D audio system is model fall off, right? So as I get farther away from a sound, it drops off. And actually, the way that this works, it's a 1/r² law based on something that is called sound intensity. Now, human perception of sound isn't quite as simple as you might think. It's not related directly to the pressure of the sound waves in the air. It's actually related to the square of that, and there's a bit of math involved. But basically, things fall off as 1/r². There's also another interesting aspect of this, actually, which I'll talk about in a moment, but different aspects of the sound, like the high frequency and low frequency components, actually drop off at different rates, and we model that as well. But for the purpose of dialogue, the problem is that if you use that kind of a fall-off curve, that realistic fall-off curve, your dialogue sounds very realistic as the character moves away from you, but you start being unable to understand what that character is saying. Now, in a game like The Last of Us, pretty much all the dialogue that's going on conveys some information, right? So if the enemies are saying things, they're talking about their perception of Joel, whether or not they're going into a search behavior, and so on. And they're telegraphing things that the player really needs to hear. So we wanted to be sure that every line of dialogue would be audible, no matter how far away the characters were. And so this is that sort of ever-present fight, in the game industry between realism and gameplay. And in this case, we chose gameplay. So we said, forget the fall-off curve. We're going to invent our own fake fall-off curve. It falls off sort of slowly near the listener, a little bit more quickly in the mid-range, and then slowly again in the distance, allowing us to provide the sense that they're either close or far away, but not having it attenuate off to the point where it was illegible or inaudible, I should say. Excuse me. Another thing we did is in The Last of Us, for all of our sounds, including conversations, is we modeled the way that sound propagates in the game. Now, we didn't actually model it, but we did some things to provide that illusion, if you will. So as you probably know, sound has multiple paths that it can take from a sound source to the microphone or your ear. It can take a direct path or an indirect path where it bounces off of the objects in the environment. And this actually gives rise to 3 different kinds of sound qualities, if you will. There's what we call a dry sound, which is the direct path. And that sounds kind of dead, right? It sounds just very like you've recorded it in a padded room. Then we have echoes, and that's when a sound is bouncing off and coming back to your ear, and your ear is perceiving it as a distinct copy of that sound, right? The whole echo, echo, echo. And then eventually the sounds bounce around in the room, and they start overlapping with one another to the point where your ear just can't discern them anymore. And we call that late reverberations, or the diffuse tail. This is what it would look like just on a graph, imagining a simple clap. Right? That would give you a single spike at time equals 0. Then you might get a few reflections, and then it all blurs together into the diffuse tail. So the trick is, how do you model that without actually modeling the path of the sound? And there are some tools that allow you to do that kind of modeling, but it's very compute intensive. So if you think about it, all that really matters is what gets to your ear, right? So if I'm in a particular environment, I'm going to generally hear a certain amount of echoes, a certain amount of diffuse tail. The shape of that diffuse tail is going to be a certain way. And by modeling that, by just encoding those parameters of how that reverb is going to sound and what the mix is, we're able to provide a sense of that room that works. Now, each room will be different, so what we did is we just annotated the game world with regions, each of which had various settings for these reverb parameters, and then as you move from region to region, we would just cross-blend and so on. And that provided a base reverb that we use in all sounds, including the dialogue. So here's
How
some
about
examples.
you let me go first and keep your voice down?
Okay. Joel!
I'm all right! Are you okay?
No! You scared the shit out of me!
So, how old are you?
Me? 14. How old are you?
The same?
Oh, you're 14, huh?
I'm close.
All right.
We need to get back out, find that bridge.
Tell me where to go.
I hate this crap.
Actually, in this room, I think it all sounds very echoey, doesn't it? Anyway, you get the idea. Play the game, then you'll know. OK. Another thing we did is we want to model when objects are blocking sounds. And there's actually three sort of categories of blockage. The first one is occlusion, where both the indirect and direct paths are blocked by a wall, let's say. In this case, you're just going to hear either a very muffled sound, both the wet and dry are going to get muffled down, or you're going to hear nothing. There might be an obstacle in the way of the direct path, and yet there may be a free indirect path. In this case, what we do is we attenuate down the dry component of the sound while allowing the wet component to still come through. And as Jonathan will talk about, we also model the fact that that wet component is going to come from that doorway up above and below rather than directly through the wall. And that gives you a sense of direction and also makes it sound as though the sound is muffled in a realistic way. A kind of rare case is something called exclusion, and this is the opposite, where the dry path is free, but most of the wet is getting attenuated. And so here's a few examples of that in game.
Oh, shit. Take it easy, man, all right?
You keep this up, I'm gonna make you real sorry. Son of a bitch!
All right, it's a little hard to tell in that last example, but you could hear that his voice sounded a little dry because it was coming through that doorway. And then as he moved behind the doorway, it switched to a very kind of wet, echoey sound. All right, another thing that we did in The Last of Us that I found, that all of our, our audio designers found really interesting as well, is the ability to call out locations for the player. This serves a gameplay purpose because it lets the player know whether or not he's been seen, and also just provides some realism. So here's an example of that.
Behind those windows! Behind the car! Behind the couch!
These guys really shouldn't be calling that out. It just gives them away, doesn't it? Oh, well. All right, so the way we did this, again, not rocket science, but really simple, but very cool, the results. So let's say that we have an environment like this. This might be the 7-Eleven towards the sort of early beginning of the game where the truck crashes right there inside the 7-Eleven. And what we'll do is we simply annotate the region. Here is the 7-Eleven store, and here is the street. We call these general regions because they provide information about just large categorizations of the space. We want to get a little more specific, so we implement some additional regions that we call specific regions, like the soda machine, the counter over here, maybe the car out in the street, or a tree. Now, what we're doing is we're basically, any character in the game is simply noting which regions they're in. And it knows what general region he's in and what specific region that he's in. And those become facts in that character's fact dictionary. This allows us to basically choose appropriate lines of dialogue based on that. And here's how it works. So let's say Joel is in the store and behind the counter. If an NPC is in a different general region, then we actually just forget about the specific regions and we just call out the general region. And we say, hey, he's in the store. But if the NPC is in the same general region as the player, then we can revert down to the specific rules and say, he's behind that counter. So just by using this very simple mechanism, we were able to get some, I think, really realistic and intelligent-sounding dialogue out of the characters that was relevant to what's going on in the battle. All right, so this sort of concludes my talk. I'd just like to give you a sense of some of the future directions we're thinking of going and some ideas for you all as you implement similar systems in your own games. I'd like to explore this handling of interruptions in further detail. We think that there's some richness to be had here. The idea, for example, of having conversations slightly overlap or having one character actually show a little indignation might actually be cool in certain situations, especially in, for example, idle ambient conversations. Maybe doing the glottal stops. Maybe injecting a little line, a little snippet of audio, that kind of thing. I think it would also be really interesting to have conversations that are interrupted, like you throw the bottle, they say, what the heck was that? And they go over there, and then get back into their previous conversation. What we would do in the actual shipping game is we would just basically start another conversation from scratch, and they would just go on talking if you didn't do it. But it'd be neat to say, as I was saying, and then have them continue on from the previous one. We just didn't have time to do that. I'd really like to explore accounting for efforts. So one of the places where our dialogue system does break down is when, let's say, Joel is saying something interesting and then he jumps over something, but he continues to talk as if he's standing there perfectly without exerting any effort. This is a really tough nut to crack. I admit that I don't have a really great answer for it right now. I mean, you could, for example, just interrupt the line, inject a little as he's jumping over, and then continue it, excuse me, or something like that. But really, it's interesting because in graphics right now, right, we're actually procedurally generating every aspect of that character. But in terms of audio, all we're doing is recording a human and playing it back. It's really sort of the Stone Age, right? So perhaps doing some kind of procedural modification of a recorded line, or even someday getting to the point where we could procedurally generate conversations that actually sound human enough, that don't sound like you know, Stephen Hawking, would be great. So once you've done that, then you have all sorts of possibilities of dynamically changing the dialogue and sort of cross-blending in some efforts and so on. So this one's a really interesting area of research that I think it would be cool to explore. A few other minor ideas, maybe doing more with complex branching in our conversations, maybe supporting an explicit AND operator just to make things a little simpler syntactically, or maybe providing macros. We actually have macros in our scripting language, but we didn't have time to retrofit them in for the dialogue system so that you could specify a rule and reuse it over and over. So we did have a bit of cutting and pasting in our system that we would have liked to avoid. And actually already for our new Uncharted game, we're starting to explore using these rules for other purposes, like selecting cameras or selecting melee moves at runtime. So once you have that rule system implemented, you can use it for all sorts of things. It's great. All right, so I think we should open it up to questions. I'll mention a few things. One, these slides, I'm going to post them up on my website, GameEngineBook.com. Feel free to contact me via email, and I usually try to get back to people pretty quickly on that. And so let's open it up. Make sure to come up, if you can, to these 3 microphones if you're asking any questions. Thanks a lot.
Could you talk a little bit about the evolution and the chronology? How many of these things were in pre-production and in concepting? How many during implementation? And then how many might have been late polished things? I'd love to get a sense of how that evolved.
Yeah, that's a great question. Definitely. We actually, early on, the dialogue system, I mean, we did have the Uncharted system, so we were able to use that to call out lines, but the conversation system hadn't been fully developed yet. And what we did is we actually used, a lot of times, because we wouldn't have recorded lines, we would just use these in-game text, right? So we would just pop up text saying the various lines. But I would say that pretty early on, we were thinking about how conversations would support the AI. And so, yeah, it started pretty much in pre-production as far as getting stuff spec'd out, but it evolved over the game, yeah.
Hey, can you give a bit more detail about how you guys marked up the specific and general regions, like the couch or, yeah?
Oh, sure. I mean, do you have, like, specifically, what
Well,
are you
was it
interested
a
in?
volume, or was it something that was attached to the object?
Oh,
or
gotcha.
How was that done?
I see, sure. Yeah, very good point. So in our engine, we just have a general region system, which is, the regions are just defined as basically a set of planes that define a volume. And so we can use that, and we use that for all sorts of things, for triggering in-game cinematics and so on. So it's actually a really simple matter of just placing these regions, and we have a tagging system in the engine for anything, and so we just put tags on to say, this is the general, this is the specific, and we just laid out a set of defined names so that the audio designers would say, okay, here's your choices for the specific, here's your choices for the general, and then go to town.
Cool. And just as a follow, so it didn't actually come with the object. So like every time they placed a couch, they had to replace the.
That's a really good point. No, it is possible in our engine to parent things together, and so you can make sort of a prefab couch that has the region associated with it. And we did that also for like traversal. There are these things we call traversal action packs that you could hook onto the couch and they could climb up over the couch, that kind of thing. So yeah, that saves a lot of effort, definitely.
Cool. Thanks.
I'm curious if you ever felt the need for conversation visualizers, or if that just ended up not being necessary.
That is a very good question. Early on when I was starting to do this, I actually imagined that we would want to put a diagram up much like I showed, right, with the timeline and so on. It turned out we didn't need it. Just using the TTY was all we really needed. But that said, the conversations in our game, although they're cool, they're not as complex as we could have made them. Right? We could have had huge, crazy branching things, and we usually avoided that just because we didn't have time to put everything in that we imagined. There's a whole pile of things on our list for like next game we're going to do this or whatever the next game might be. So so there's maybe when we get even more complicated things we'll want a visualizer, and that's the way we do things at Naughty Dog generally is, necessity is the mother of invention, and so we'll only make the tool when we really start needing it, when people are feeling bogged down.
Yeah, going back to that, this tree for your dialogue, your conversation, would you go back after each step through that tree, go back to the root and travel down to find the next piece, or would you return back to that node and traverse that subtree?
Right. It's basically what's going on is it's tracking where you are in the tree as you go, and so the rules are evaluated for the root, and then let's say it goes to branch A, then the rules are only evaluated for A at that point, and they branch on. The reason for that is that once line 1 has been said, usually it may not be relevant to go back and say some totally unrelated branch. But it's a good point. There might be cases where we might want to loop back around and just reevaluate the whole thing. And you could do that now in our system by setting a next segment pointer to point back to the beginning and then reevaluate. But we found we didn't need that for our cases.
Hey, in regards to your dictionary of facts, is that something that you guys determine at compile time or runtime? Like, are you guys adding and removing facts as the game progresses?
Yeah, it's all runtime, and actually the reason for that is twofold. One, the AI needs to be able to populate that and change it. Like my health, for example, needs to constantly be changing. The set of keys that are allowed in the dictionary is also not fixed at compile time because they're just string IDs. So they're literally just strings that have been hashed. So it becomes very, very flexible. And it means, actually, that audio designers can just invent their own keys and stick them in the dictionaries without the programmers ever even knowing. And that was great. They did that a lot. And actually, there were a few cases where I looked at something, how did you guys do this? And I looked, and that's cool. They just invented a fact that I wouldn't have even thought to do. So, yeah.
Okay, that's awesome.
Runtime's the way to go, yeah.
Hey, just one of my things was just about bigger picture, general frequency. I feel like you guys just nailed like how often people are talking. And I'm working on an adventure game kind of thing. We carpet bomb with a bunch of VOs and stuff like that, and then it's like, oh, there's too many. You remove a couple and say, oh, now they're never talking. Was it just replaying the game and just going back through like that, or was there like a magic number like, hey, it's been 12 seconds, that's too long between VOs? Like, how was...
Right.
Yeah.
Yeah, no, that is a really, really good point. And I would love to say that we're just all like mega brains and we just knew and we did it right, but no. Everything we do at Naughty Dog, it's all iteration. It's all blood, sweat, and tears. And so we literally just played encounters over and over again. And I mean, Max will be talking about this in his talk this afternoon, but he would sit down with Bruce, our game director, and they would just go over and over the same encounter, trying to tweak how often things are playing and spacing and so on. And then Neil would be writing the arc so that, the arc of the story, so that when there's tension and then you want something that relaxes you for a while and so on. So the whole thing was very carefully crafted, but it took a lot of effort. Yeah.
So no easy shortcut.
No easy shortcut, sadly, yeah. Maybe someday tech will answer that problem, but I doubt it.
Hello. So do you think the rule-based system would be a good basis for an interactive conversation system where the player selects the next line? Or would you ultimately start hitting limits on how complicated you could make the entire conversation?
Well, I mean, I think it boils down to, so if you imagine, you know, I don't know, like an RPG-type game or something with really big branching conversations, the fact is, at some point, an audio designer and a writer need to get together and figure out what all the possibilities are. Once they've done that, you just encode that in your rules. So yeah, I would say yes, you could totally use this for an interactive system. It really just boils down to how do you manage all that data. And our text file system works pretty well, but maybe when you get really complicated, as the other person was saying there, it might be a good idea to have some visualization tools or some other UI overlaid on top of those files so that you could manage it better. But yeah, I think it would be fine.
Okay, cool. Thanks.
Hello. To what extent do you share the facts with translators and voice directors for localization versions?
Now that's an excellent question too. So there's a whole untapped area here of having different things happen depending on what language you're playing in. I don't know whether that's something that's desirable or not, but it's interesting to think about. I would say that, I mean, our philosophy is the experience should be the same in every language, and we're just translating the lines. So the way we actually do that, I didn't talk about it in my talk at all, but the physical lines that are laid out, we record them in English first, just because that's the language we're all speaking at Naughty Dog, and then we have a bunch of companies that we work with, outsourcing and so on. We have a centralized database of all of these things with a web interface, so it's really convenient for outsourcers to go in there. And then they'll go and they'll record and set out and also put in subtitle text for every single line. But we don't want to, at that point, mess with facts or have things branching in different ways in different languages, because it would be kind of a nightmare. But maybe for some game, it might actually be a really interesting thing to try. So,
okay, thank you.
Mm-hmm.
Hi. When you do a priority interrupt with a higher priority dialogue interrupting a lower priority one, do you have some intelligence or algorithm for figuring out where to interrupt that prior one? I mean, you don't clip in the middle of a word or something, do you?
Well, actually, we do. And it turns out the kinds of interruptions we do in The Last of Us, like I mentioned, you know, we started by kind of overthinking it, and then we tried just cut it off and see if it sounds good. And in almost every case, it sounds fine. The reason for that is the kinds of interruptions that happen in our AI systems are usually going from one major state to another major state, right? So, like, I'm talking about, yeah, we killed 2 guys last week. It was really hard. And then suddenly, boom, I see the player. Combat breaks out, right? So the previous conversation didn't matter, and you just cut it right off, and then something really high priority is happening. But it's a good point that you might want to, in some systems, be able to do that, and it would just require memory, right, where you could say, this request has come in, store it in memory, and wait until an opportune time to actually trigger it. We do that in animations a lot, but we don't do it in conversations. So.
Thank you.
Mm-hmm. Okay, this has got to be the last question because we are over time, so go ahead.
Again, regarding interruptions, whom do you interrupt? Is the person talking interrupted, or do you choose between the person he's talking to? And who it says the line that you need to?
Yeah, well, so who says the line is defined by speaker and listener, and that's defined by the AI code. And then it just cuts off the entire conversation. So whoever happens to be speaking at that moment is interrupted, and everybody else just doesn't say the rest of their lines if we're going to interrupt. So. All right, so there are breakout rooms. Also, remember to do your evaluations, please, because it gives us a lot of good information about how to improve the talks in the future. I'll be in the breakout room over there if you've got further questions or if you just want to shoot the breeze. Thanks a lot.